when you ask some people where the power comes from, they look at the wall socket, but in reality, it comes from a larger place like this. And it gets to your house using high voltage transmission lines, typically around 500,000 volts, goes to a transformer that's in the neighborhood, and then it gets to power lines that are near your house. So the path is power generation, get it to high voltage, transmit it, get it down to more reasonable voltages, put it on power lines, and with a transformer, get it down to the voltage that you actually use, which is 240 volts. I have a sidebar about history. In the late 1800s, Thomas Edison built coal-fed power plants that generated electricity to light cities. And small cities, small systems would power cities, but they couldn't go very far because direct current couldn't make it very far efficiently. So a think tank of the world's brightest minds met in London to develop a system to distribute power efficiently. Against the advice of Thomas Edison, alternating current was selected. And Nikola Tesla created an effective system. George Westinghouse developed the system, and so it became the standard. Although AC is more dangerous to people than DC, it was very efficient, so it was selected. Now, because it's dangerous to people, some thought that, we could build this electric chair to kill people instead of hanging, which would be more humane. Whether it is or not, I don't know. But anyway, language is a dynamic thing, and it has new words once in a while. Some words change. So they needed a word to describe what they do when they kill people with electricity. So some of the choices were electromort, ampermort, and since Westinghouse was a big favor of AC, one of the choices was Westinghoused, electricide, and finally electrocution was selected. Now let's talk about the sources of power. There's fossil fuels, we all know about that, and all these sources have some kind of environmental impact, some more than others. Coal, as you know, is bad, coal, oil. Natural gas isn't quite so bad, but it's still bad. Hydro is not so bad, although it impacts fish. Nuclear doesn't generate carbon dioxide, but it has pretty bad environmental issues. Geothermal is not bad, and I understand it does have some environmental issues, but I'm not too familiar with that. Solar is pretty good, but it's intermittent is the problem. And I found this in a magazine showing the output of an array in the summer in Arizona. And look at those dips. Dips here, dips here. So while it's in a dip, something else has to be providing the power. So the fact that it's intermittent is a real problem. And also with wind, it is also intermittent. I don't have a graph of what it does during the day. One of the bad things about wind, people say it kills birds. Yeah, it kills birds. But the biggest killer of birds is cats. And the second worst is buildings. So it comes down to storage. We really need storage to take care of the intermittent nature of these renewable sources. Batteries are a good choice, but they're expensive now, and a lot of work is going on it, but it's still expensive now, so there's not a large amount of it in use. Another source, which is not very common, but is elevated lakes. If the geography allows you to pump water up a lake, then you can convert energy into potential energy by pumping it up the lake, and then when you need the energy, you can run it back to your turbines. And years ago, when I visited Grand Coulee Dam, I saw these pipes that they used to pipe water up to a lake. And those are huge pipes. Look at the size of cars down here. So they can pump a lot of water up to the lake and use it later. With increasing use of subsidized solar and wind energy, the old-fashioned method of running a power company has changed significantly. Obviously, the power company has to provide 100% of the power, 100% of the time, and they have to keep profitable, even though they're getting inexpensive energy from wind and from the solar cells. I'm going to have another sidebar. I made up this story to describe the challenges of a power company when they have to deal with these new sources of energy. Okay, I have a 6-person band. I play at a pub, and the pub owner says, you know, we have a school in this city, and there's a music class, so some of the people want to experience playing in a band. So I said, okay, I can have 3 people. So the students, who are subsidized by their parents, come and play for free. So they come, but they're intermittent because, you know, they have classes and sometimes they can't come. Sometimes they have to leave in the middle of a gig because they have something important, like dates. So you know, so I have to deal with it. I have to keep my band, pay my band every night. Then the pub owner says, you know what? You're getting folks for free, so I don't have to pay you for those people. But I say, but I have to pay my band all the time because I have to have them. So I have a financial dilemma. And that's similar to what the traditional power companies are dealing with, because they have to be profitable, they have to provide all the power when needed, and they have power sometimes when they don't need it. So that's a problem. So a good storage plan is needed. And with some cities or states are saying they're going to be on 100% renewable by a certain date, you got to have the storage capability. I want to talk about power supplies. And I'm going to use a water analogy to start with. Electrical engineers in the audience may be horrified by these, by these analogies, but let them be horrified. We'll have fun. Okay, suppose you need water. So you hire a person to haul 5 gallons of water every minute, and he does that. But the problem is, you know, you have water for a while, and then it runs out. So that's no good. You have water just part of the time. So you're pretty smart. So you say, I know what? I'll have a tank. So now you have water all the time, but the pressure goes down every time until he comes back and he gives you more water. So again, you're smart, so you say, okay, I can have a bigger tank. So now the pressure variation is smaller. And if you want it even smaller, you get an even bigger tank. So that works. But you're real smart, so you say, I want a whole new system. Supposing I have the person deliver water 5 times as often. So now the 5-gallon tank can be a 1-gallon tank. So then the variations up here would be more frequent, but the variation will be smaller. But then you say, enough of this. I want it really efficient. I want the deliveries to come much faster than once a minute. So even 5 times a minute is a little better, but not very good. So how about 500 times faster? Then the container can be very small. And so when you think about the original 5 gallons versus doing it 5 times as fast, then you end up with a little container like this instead of a 5-gallon jug like this. So the thing about this is you can mechanize it, and you don't have a person bringing it every minute. So that works. Now I want to talk about an electrical power supply. This is a traditional power supply. You take a transformer, primary, secondary, and then you put it through a rectifier. A diode is a device that allows current to flow in one direction but not another. So you get an output like this. Kind of like the water and the funnel thing. You only get power part of the time. So you get a tank, a storage, a capacitor. And again, the voltage goes down, up and down. And just like before, you say, I want a bigger tank. So you have more capacitance. And now the voltage varies less. And also, if you want it to vary even less, you get even a bigger tank or a bigger capacitor. So here's an example of a stereo amplifier that uses a circuit that's similar to what I described. Here's the transformer, here's the capacitor that stores it, and then the rest of the circuit runs on this voltage that comes from this transformer and gets stored here. And these transformers are used to couple the output from the vacuum tubes to your speaker. Capacitors come in various sizes, and I'll have a box there showing these different capacitors, big ones, little ones. For those of you who do repairs on electronic things, one interesting thing I found is that when you see a capacitor that has a bulge like this one, that's a bad one, so you better replace that one. And I replaced 2 or 3 of those on a digital video recorder that I had. When you need more power, you need to have a transformer that's bigger. And here's an old-fashioned Tektronix oscilloscope, and here's the power transformer. And you can imagine that it's pretty heavy. So you're just stuck with that. You have to have a big transformer for the power. And the only way to get around that is to build a high-efficiency power supply. So what you do is, well, here's another transformer, and probably most of you have it in your house because it runs your doorbell. So obviously, transformer comes in different sizes for different power needs. And also for the older cars, you have this transformer that makes really high voltage for your spark plugs. One thing I need to point out is the transformer provides safety isolation so that it's unsafe on this side, and on this side it's safe because the way it's built, there's enough spacing between the primary and the secondary that doesn't allow current from this side to jump over to this side. Now we're going to do a high efficiency supply. You first start out by rectifying the line directly. So you have a rectifier and you have a DC voltage here. And it's pretty high voltage because you're taking the line voltage and just rectifying it, and it shows up there. And in Europe, it's 240 volts, so this will be, maybe like 300 volts or so here. So you start out there without a transformer. And then you build a circuit. It's a lot more complicated than I show in the little box, but you build a circuit with a small transformer now because it doesn't need to be big like the 60-cycle one. And the frequency could be maybe 500 times faster than 60 cycles. The exact frequency doesn't matter, but that's roughly the rate. And then you end up with a low voltage circuit output here. Now this is an example of a smaller transformer. These also come in different sizes. When you have when you have low power requirements, then it can be really small. Whereas if you have a slightly larger power, it needs to be proportionally larger. And the transformer also provides, just like the 60-cycle one, has to provide safety isolation. Now, there's a lot of circuits on the left side and a lot of circuits on the right-hand side of this transformer. And when you build an EC circuit board, you need to make sure that the parts and the runs are separated so that you don't have any leakage that causes unsafe current to flow on this side. And a lot of methods could be used. One is to, if there's an area where there's primary and secondary, you could actually cut a notch in the circuit board so that in order for current to leak, it has to jump over, which is not going to be very easy to do. So maybe I'm getting ahead of myself, but when you look at inexpensive supplies that's made by people, unknown people, you may wonder whether they're using good standard procedures to keep the spacing from the primary side separated from the secondary side. Now, products generally need multiple DC voltages. So generally you have one main supply that generates a low voltage. It could be, moderate, like 12 volts or 15 or whatever. And then you could apply that voltage to additional power supplies to generate different voltages that you need. And one good example is the CPU. It generally requires low voltage, like 3 volts, or sometimes it's even lower than that. But that's one good example of having a secondary high-frequency power supply. So here's a list of, here's some power supplies that you're all pretty much familiar with. This is the MacBook supply. And I threw in this traditional supply here, just to make a comparison. You notice that it's about the same power as this one, but it weighs 10 times as much, and it only runs on 120 volts. These all run on 100 to 240 volts. So you can use these in Europe without any trouble. One of the things that is attached to power supplies is some kind of listing of certification of things. Like here's United, I can't think of it right now. Underwriters Laboratories, and then this is in the case Canada and US. And this is an additional certification called European Conformity. And this has more requirements than UL, and some of them are more difficult. Well, they're all more difficult to reach than the UL. And some products have this ETL certification. Now here's a Apple supply and a fake. You notice that this one says designed by Apple in California, and this one doesn't say anything. This one has UL, and this one has Circle M. I looked and I couldn't find any definition what Circle M is. So maybe it's something, but maybe it's not. But it is not UL, so be cautious. So when you're at Free Geek and looking at this box of USB power supplies, make sure you look, well, bring your magnifying glass, first of all, and look to see that it has a UL listing.
I noticed both of them have the same model number.
Pardon?
Both of those have the same model number, which I thought.
Oh yeah, they've done a really good job of copying all this stuff. This logo, all this in about the same place too. So it's hard to tell that it is different unless you are looking for the sentence up here.
So did you pop the end off or something? I never remember seeing.
I'm sorry, I can't hear.
Pop like the end off or something?
This is straight action.
I am having a hard time hearing, so would you say it again?
Well, I was just, when I have never seen that, so they say I just have to get a magnifying glass out.
Yeah, you have to have a magnifying glass out, yeah. Here is thanks to Josen, a laptop power supply with the cover and the shields taken off. So there's a lot of parts in there, And you know that every part in there is there because it's needed. They're not going to put parts just for fun. So everything there is needed. So you could buy a fake one, and they don't have many parts, and you wonder how they get away with it. So maybe it'll work, maybe not. Well, maybe you plug it in and it works, but I get concerned about things like my safety, because they may not have done a good job of their design. Now, everything has a downside. The high-efficiency power supplies generate a high-voltage waveform that they apply to the transformer. So, for example, if you're in Europe, this voltage could be 330 volts, and you have this signal going up and down at what was that, 500 times 60 hertz, So it's high frequency, and it generates noise, radio frequency noise that can get into TV sets and other electronic things. It also generates signals that can get back into the power line. And there are rules about that too. So you have to build a filter to make sure that signal doesn't get back into the power line. And when you think about this, think about maybe a person in the next room playing the low notes in a guitar, and you say, well, you know, it's smooth, so maybe you hear it, maybe you don't, but if you do, it's not very distracting. But if that person is playing a snare drum or cymbals, you know, those audio signals have really sharp edges, and you can hear it. And it could be irritating, and if they're good, it's not irritating. But anyway, that's the thing with this. So you need to shield the power supply so this doesn't get out. And these days, with a lot of products built in plastic boxes, you have to build the shields inside. In the old days, when you have a metal box, that was pretty good. You know, you can shield it easily. So here's an example of a filter that keeps the signals from getting out to the power plug. And here in a supply, an old-fashioned supply, there was some filtering in this unit, and also here's the coil and the transformers. You can tell that this is an old supply because you can actually see the resistors. Because if this were done in this year, you would have to have a magnifying glass to see the resistors and the small parts. So this is just symbolic, but this is to show that you need a filter. What happened here? Oh.
Not that one. That's okay.
Oh, I see.
Sorry.
Thank you. I can just put this here.
You mind moving your foot there? Thank you.
All right. So this is just symbolic to show that you need a filter of some kind. And here's a picture of the MacBook supply. And some people have put energy into figuring out what kind of shields needed to be in place. And this is the back panel of my second to the last product at Tektronix. And it has a CE qualification. And it means that it cannot radiate signals. And we have to provide the shielding for it. Not only is the power supply whipping around, we have circuits, you know, like microprocessors and stuff that run at high frequencies and generate all these signals. And, you know, when you think about antennas, you think about an antenna up in the air and whatever. But on the circuit board, there's little bitty antennas that radiate these things. And so we spend time tearing our hair trying to figure out what can be done. Usually this is toward the end of the project, and management is breathing down our necks, and we don't have the freedom to redo a whole bunch of stuff. So we work hard. So analog hardware engineers, we work hard for our $1 million salaries. And software folks do pretty well, but we have a way to keep them focused. Next, I want to talk about power quality. By the way, for those of you who actually believe the $1 million part of the story, I have some snake oil to sell you. Really good snake oil. Not only is it organic, it's free range. So see me after the meeting. The main power quality problems are blackouts, brownouts, voltage spikes, and sustained over voltage. Blackouts is simple, you know, the power goes out. And what do you do about that? Well, you can use something like this. APC is a good brand, and they've done a good job of generating signals when the power goes out. So this is an example of what the waveform could look like. You know, power's coming in and the power stops right here. Then the inverter comes on, it runs on batteries, and it continues the 60 cycles waveform until the battery runs out. Most companies are good, but some are not so good. Here's a picture of what a triplet output looks like. So when the power stops, it says, oh, I'm going to have to turn on. So it runs at about, 400 cycles or 500 cycles per second, and then finally it gets to be 60 cycles. So maybe your product will be okay with this, but maybe not. So better stick with something like this, which is pretty organized. The other problem is voltage spikes. And by voltage spikes, we're talking about very short spikes, much less than 1,000th of a second. And it can be pretty large. The standard spike definition is 6,000 volts. So it comes by having lightning hit the power lines. Sometimes it hits the ones that are far away, and sometimes it hits power lines that are closer to your house. And so it gets through transformers and whatever, and it ends up at your house. What do you do about that? Well, you get a surge protector. Not only that, you get a good one. And APC makes one, and this is the model number, P11GTV. It sounds like I'm a marketing person for APC, but I don't have any connection with them. One thing to look for, and they're not always specified, is a thing called feed-through voltage. It means that when 6,000 volts is applied to the connector, what shows up here? And here it says 300 volts. So, it's not bad because European power is 240, so it's not far from that. MOV devices are generally used to clamp the spikes. What they are, it's a weird device. It's a device that when you put a certain voltage above its rating, it conducts like a short circuit. And then when it does, it's sacrificial. So it burns up part of itself. And so the more pulses get applied, the more it burns up and the smaller it becomes. And with surge protectors, you often see ones like these, about a whole bunch of them, like 4 or 6 of them, all hooked up in parallel, so that when one gets deteriorated, the other one can take over. Another device which has better performance but is expensive is a line conditioner. This works very differently than surge protectors. Instead of clamping the circuit, it isolates it. So it blocks the pulse from getting to the secondary side. And so it needs a transformer, a very special transformer. And they're quite expensive, although you can get it on eBay. But be careful of the shipping because they are quite heavy. Oh, there's a story about these. I worked in a building where on one end there was the big computer room, the corporate computers, PDP-11, 70 by Digital Equipment, and an IBM 360. They did payroll and inventory, whatever. It's in a locked room and all that. And in our group, we had 2 PDP-1140s, and the previous year I was able to talk management into letting me buy a couple of these for our computers. Well, one day, the light went flicker, 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 and it was less than a second. And it crashed the 360, and it crashed the Digital Equipment, PDP-1170. And I'm thinking, holy cow, here's a computer that's running, payroll and inventory for $1 billion company, and they haven't figured out how to protect it from spikes and things. Of course, our computers in our room worked fine. There was nothing that any of the software people noticed, because I went and talked to them and they said, what? Nothing happened. So these really work. The other problem is sustained overvoltage. Now, when a car runs into a pole or it's winter and the poles fall down, the 7,000 volt lines falls on your 240 volt line. And yeah, the utility company has circuit breakers somewhere and whatever, but it takes a while for them to be activated because they're probably quite a few blocks down the road. So you need to have your surge protector protect you from this also. And what it'll probably do is not just have the MOVs clamp the spike. Well, it'll clamp it for a while, but then it'll blow the fuse. So that's a good thing. These are MOVs again. Oh yes, tubes. Yeah, in the old days, you put a signal on the grid and you get an amplified signal on the plate. Well, in 47, a transistor was invented, and it was obviously a very primitive transistor, but it did work. And symbolically, it's kind of like this. You put a signal in the base, and the amplified signal comes out on the collector. Here's an example of a alloy junction transistor, and it looks like it's handmade, so you don't make those in high volumes. Of course, some of it could be mechanized, but still, you can't make it in high volumes. So some bright people came up with a process they called a planar process, where they take a semiconductor material, usually silicon, and they put negative charges into it. And then they put a photomask on top of it and bombard the surface with a chemical to make this area positive. So now the end charges are still there, but there's enough of the P that it overwhelms it. Kind of like putting a little lemon juice in a glass and it's sour, but you put a lot of sugar in it and it's sweet. The lemon's still there, but it's sweet. So they take this, they go on and do it again. And then they make an N, they do an N here and a P here and an N. So now you have an N, P, N transistor. And with more masks, you allow metal to be evaporated on these areas. So now you have contacts that you can actually connect to the device. And being a planar process, you can make a whole bunch of them on a single wafer. So that's a great thing. You can mechanize it, and you can have a wafer full of transistors, and you can put them in packages of various kinds. And if you want a transistor that has high power, then you put it in packages that are large so they can dissipate a lot of energy. And then the more bright people came up with the possibility of building resistors and capacitors on top of the silicon wafer. And then now they can, instead of just building transistors, you can build circuits. So you have transistors and you have resistors and capacitors, and then you can have interconnects, and then you have, now you have a circuit. So that was the start of integrated circuits in 1957. So here's a picture of one where the top has been dissolved off. So I said that this is going to be brief. I covered the invention of the transistor and the up to the development of the integrated circuits in only 14 sentences. Now with circuits built on a wafer, you can't do it. You can't check it with the old-fashioned way, you know, with a scope probe and a voltmeter and whatever. You need a specialized probe and a microscope to look at the circuit and to see to look at the wiring and see that it's working. Now, when they build circuits, they want to be able to reject the bad ones as quickly as possible. So what they do is they take a wafer prober and probe the pads of the integrated circuit and run signals through these probes to test the device. So they can power it up, they can run signals through it, and to see if the device is good or not. And if it's bad, they squirt some red ink on it, so that marks that it's bad. In my previous life, I worked on a product that developed the signals to test that device. The thing about manufacturing is time. You want to do things fast. So you get the wafer, you test it with a wafer prober, you cut it up in chips, you throw away the bad ones, and then you put it in a package. So, and for every device, they have to put wire bonds. You know, they take the pads on the integrated circuit and attach it with gold wires. And it's mechanized, but it still takes time to do. So again, that's why you want to throw away the bad ones as early as possible. If your yield was 100%, then that's not a concern. But you know, yields are not always high, and that's something that is a very kept secret, because you can't ask Intel, you know, what's your yield on a model blah 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 microprocessor? They're not going to tell you. Who knows? It may be pretty high, but and so when it's finished, it looks like that.
What is the logic between going from the gold to the lead?
Say again?
I see the gold connecting.
Yes.
And the lead after that. It seems like it kind of defeats the conductivity. What's the reason for both, the lead and the gold?
Oh, gold is a very good material. In the past, they tried aluminum, and then and it worked for a while. But then they found that what did they call it? They call it purple plague, where the bond on the integrated circuit grew a purple thing around it as it corroded. And was that your question, or was it?
He's answered it, actually. I was misreading the word.
Yeah.
Lead or lead?
Lead.
On the last slide.
It's called lead frame. You know, usually it's a chem milled part of bronze or something. So that's the term they use, lead frame.
What about copper?
What?
What about copper?
Copper, they have not tried copper. You know, gold is pretty good for many reasons. Yes, John?
Yeah, but gold, like, would be on the lead frame, would be microns thin.
Oh yeah, it'd be really thin.
Not solid gold.
You know, this would be some kind of metal. I don't know what it is, but it'd be gold plated, and
And
have
the wires be like 1 mil diameter.
and it'd be real tiny wires. Yeah. So, in summary, for blackout protection, use APC. Voltage spikes, use the surge protector. For best protection, use ONIX supplies. Use Apple supplies. Now, if you're, like I say, if you're at Free Geek and you have this box of USB supplies, you know, look through them, but pick good ones, like from Samsung or, who knows, Intel, whatever, these big companies, because they would they would do a good job because their products are on the line there. And be aware of incompatibilities. There's a really strange one that I ran into. I have a backup flip phone, real simple flip phone. I plug it into one of the Apple supplies and it wouldn't charge. Must be the cable. So I replaced the cable, no, it wouldn't charge. Plug into a different brand of supplies and it charges. So I have no idea. It charges all the Apple things, fine. When there's a blackout, by the way, I recommend unplugging your devices, like your TV set, your microwave oven, whatever, because when the power comes on, probably there's a spike associated with it. Because you can imagine, turning on the power to a whole community with a switch. So, and again, look for the UL symbol.
So Fred, I have a question for you.
Yes?
I understand why we use AC. It's as opposed to DC, it's much more efficient. What's the difference between US and Europe, 120 versus 240? Is 240, what's more efficient, which is cheaper? I understand 240 is more dangerous than 120.
Right.
But why does Europe use 240 and we use 120 or vice versa? What is the rationale?
I don't know the answer to that. I didn't research it. But,
Okay.
And in Japan, there's places where it's 100 volts instead of 120.
That depends on which side of the island you're on. I guess.
Yeah, right.
Two
So,
different
yeah.
systems.
Yes, John?
The 240 volt allows you to use thinner wires, so that way it's cheaper.
More efficient.
More efficient because the current can be smaller, because power is you multiply the voltage times the current, gives you the amount of power. So if you double the voltage, you can cut the current in half.
So it's more efficient.
Yeah.
Is it more dangerous than?
Yeah, because it will kill you faster.
Kill you faster.
But
Yeah,
it
that's,
also integrated it better. So if you look at the plugs, on ours, US plugs, you've got the two metal prongs sticking out.
Right.
Well, in Europe, they've got bigger prongs because they're insulated down here, so that you're pulling the plug out, you don't have any live metal parts. Temporarily. Yeah. And Japan also has 100 volt, and sometimes the frequency is 50 hertz, and other places it's 100 hertz, or 60 hertz.
60 is,
Yeah.
any other questions? Yes,
Edison and Wilk and Westinghouse, personally, they knew each other, and they
Right.
really disliked they had a big fight, and so Edison would electrocute horses, and he was calling the electric chair the Westinghouse chair, just to make it sound like the AC was really dangerous. But the
And-
big
and-
advantage was you could transmit the electric power long distance.
right.
So you could go from Oregon City, where the Willamette Falls is, PG, you could get it all the way here to Portland. You couldn't do that with the DC system.
And the thing about AC versus DC is that AC affects your heart. DC will burn the flesh, but AC will disturb the electric signals in your heart and makes it stop or do weird things. So that's why it's more dangerous. Yes?
I worked in a hospital in San Francisco. I'm sure some of it is still around, but they had DC current as well as AC current running through the place.
Is that right?
Yeah, you just didn't know what you got into. But most of the equipment worked without any trouble.
Oh, interesting to hear that. Yeah, because you plug an AC device into a DC outlet and it's going to burn it up. So I hope they had different kinds of plugs so that you couldn't do that.
Steve Wozniak, when they were designing the Apple II computer, he put in a switching power supply, and that was one of the first uses, or first computers that had a switching power supply.
Well, thank you. This has been interesting presentation.